Welcome, everybody. Thanks for coming today. My name is Gianmassimo. Most of you know me, I guess. The Pro Vice Chancellor and Executive Dean of the Faculty of Science and Engineering. Second longest title to Hans Sainz, my deputy, who puts deputy in front of everything. Well, I'm delighted to have everybody in for the inaugural lectures today. And I'd like to welcome everybody on behalf of the faculty and myself, and also bring greetings from the VC, Paul Boyle, who sends his regards, and he wasn't able to be here today. This is an inaugural lecture held in a proper lecture theater, as it were. This is so traditional. It's wonderful to give it here, but these are chances to celebrate personal and professional milestones for our newly promoted colleagues, and in the presence of other colleagues, friends, mentors. Don't see any family members here, but maybe sometime. And really for the university to celebrate this, the great achievements of being promoted. So today this lecture's Professor Gianmassimo Tasinato. He had his PhD, got his PhD in Trieste, Italy, and then did postdocs all over Europe, essentially, before settling in Swansea the same year I did, actually, in 2014, in the physics department. And I've also had the opportunity to work with Gianmassimo for a number of years as department head, and really enjoyed that, our interactions. Well, after the first detections of gravitational waves in 2015, Gianmassimo really focused his research, on gravitational wave cosmology. And so we're excited to hear about that today. So I'll hand it over to you, Gianmassimo, for your talk, Probing Our Universe with Gravitational Waves.
Okay, thanks a lot, Ken, and thanks for being here. And I would also like to thank the Faculty of Science and Engineering for all their support over the past few years. So let's go to discuss a little bit about science, about physics, and about the new opportunities that gravitational waves are and will be offering us in order to understand the properties of our universe. So let me just introduce from the beginning what are the topics I would like to cover. So what is cosmology? Cosmology is the science that tries to understand the properties, the overall properties of our universe, in particular the geometry and the content of our universe. Our universe expands. It started at a certain time. We would like to understand the initial conditions of our universe and what made our universe to start. We would also like to understand what is the content, the present-day content of our universe. Not just the local content, but the content, the full content of our universe. And what governs the expansion of the universe. Indeed, by looking at the cosmological observations, by looking at the cosmos, there are big questions, big mysteries that, of course, humanity always asked, but now we can address with science. The first question is, how did our universe start in the initial conditions? What is its content? And also, what will be its future? Will it always expand? Will it contract? So these are kind of questions that are very important, and it is important to try to answer. First question is the initial conditions. I just told you. So let me tell you a little bit about the second big question is the universe content. So present-day cosmological observations are telling us something about the present-day content of the universe, and what we know is that around 5% of our universe content is made of normal matter, of ordinary matter, the atoms that form the Earth or solar system or our galaxy. All the rest is something that we don't know. There is a big fraction that is some form of matter that does not interact with light. It is invisible to light. It is called dark matter. And there is an even bigger fraction, around 70%, that is not even matter. We describe it as a fluid. We call it dark energy. And what we know is that it makes our universe to expand in a special way, in an accelerated way. These are what present-day cosmological observations tell us. We have a way to, let us say, to parameterize this dark matter and dark energy, but we cannot understand it. We cannot understand it microscopically. We don't know what are the constituents of these forms of energy. And then the last big question is, what will be the future of our universe? Of course, as humans, we should not care about what will happen in 10, 20, 50 billion years, but it is, as scientists, we are curious to know what will happen. Will the universe stop expanding and start to contract? Will it expand at a constant rate, or will it expand faster and faster as time goes on? So you see, these are very deep questions that is interesting to address. So past few years ago, 7 years ago, there have been a very important experimental breakthrough. That is the first detection of gravitational waves. So what are gravitational waves? Gravitational waves are ripples of space-time that propagate. It's just space-time itself that makes this kind of waves. They are a prediction of Einstein's general relativity, and they were detected around 100 years after Einstein elaborated his theory. Why it is so difficult to detect them? Because they interact extremely weakly with matter. So their interaction rate is extremely small. Of course, at the level of experiments, this is a problem. At the level of theory, as I will try to tell you, it is an advantage because it means that they can travel without disturbances over very large cosmological distances. So in the picture there, you can see the coalitions of two black holes. They form these waves that propagate, and they have been discovered by interferometers, like the one in the upper figure, and this is the kind of figure, the figure of the detection. These are the waves. So these are two signals observed in two different detectors in US. This was the first detection. Okay, so at the level of physics, gravitational waves are not so different from electromagnetic waves, from light. Also, light is described in terms of amplitude or wavelength or frequency. And what we know is that the electromagnetic spectrum can span a very large, very broad range of frequencies, from radio waves, microwaves, to X-rays and gamma rays. Each frequency band is called in a different way, and the visible light is a small fraction of these frequency bands. Okay, so let's go to gravitational waves. At the level of physics, they are not so different. And what is interesting is that also there are different frequencies for gravitational waves, depending on their sources. And now the community is really pushing a lot to try to cover experimentally all the frequencies possible for gravitational waves, depending on their sources. So let's give a look to this kind of plot. Here is the frequency of the gravitational wave. Here is the amplitude. So what we observed so far are gravitational waves in the frequency of the order 10, 100 Hertz, with kind of interferometers like LIGO Virgo. But there are many other physical phenomena that predict gravitational waves with different frequencies. And now scientists are trying to think how to detect different frequencies of gravitational waves. And this is precisely where a lot of effort is put in the community. So from my side, here in Swansea, I am part of a collaboration that is called LISA, that whose aim is to try to detect gravitational waves at the frequency of the millihertz. That is interesting for reasons that I will tell you in a while. But before doing that, I want to tell you a little bit about what is LISA. This is an experiment that will take place in space. It will consist of three. So here, there in the upper table, what you see in blue is the Earth that rotates around the Sun. And you see a big triangle that is following the Earth. So that big triangle is the experiment LISA. It consists of three spacecrafts. You can see there the description, that are separated by 2.5 million kilometers each. And there will be laser beams that are sent from one spacecraft to the other. If a gravitational wave passes through the experiment, it will slightly modify the propagation of light that passes from one spacecraft to the other. It will modify the signal and it will reveal its passage. So this way, we are planning to detect gravitational waves. So you see the launch of the experiment will be in 15 years from now, but it is extremely important to start to work on the science that we can use, that we can do with that. Indeed, we can observe important astrophysical phenomena like the merging of supermassive black holes that are at the center of galaxies. When galaxies collide, they emit gravitational waves in the frequencies of this experiment. And there can be also other important information about cosmology. So indeed, we are already publishing papers. Here is a paper that I did with around 100 co-authors. So here is me. But yeah, it's alphabetical order. But you see, there is a lot of activity even for experiments that will take place in the future. For young people, it's not so distant. So there are also other experiments that will take place. Another experiment is Einstein telescope. It will be an interferometer, but not on the surface of the Earth. It will be underground. It will be a big triangle underground. And what is interesting of this experiment is that it will reach sensitivities that are much better than present-day ground-based experiment. And precisely this morning, Swansea University we entered into this collaboration, Einstein telescope collaboration. And another super interesting way to detect gravitational waves is to use some astrophysical objects. In particular, there are neutron stars. Maybe you heard about those. So there are neutron stars that behave due to their internal magnetic fields. They behave as pulsars, so they emit light. So they rotate, they emit light so their rotation rate is extremely precise. So they emit light. The idea is that in the Earth, by observing the light that comes from these pulsars, we can reveal gravitational waves. Why? Because gravitational waves that pass through the space-time, they can modify the space and change the detection, and change the period or the observed period of pulsars, because if a gravitational wave deforms the space, there is more space for light to travel, so it deforms a little bit the period of pulsars, and by correlating, by putting together signals from different pulsars, one can reveal the presence of gravitational waves. This is why I tell you this, because recently, past year, there have been preliminary hints of detection of gravitational waves with this neutron star that is called pulsar timing arrays. So this is the kind of setup, gravitational wave science. So in the last part of the talk, I would like to tell you a little bit why gravitational waves can then be used in order to solve these big mysteries of our universe. So the first one is the mystery about how did the universe start. So we do have a very, very compelling theory, that is called cosmic inflation, that seems a promising way to understand the initial conditions of our universe. From the point of view of a theorist, this is super interesting because it puts together quantum mechanics and cosmology. The universe at the beginning was very small, so quantum mechanics, that is the physics of the very small distances, becomes important. And what happens is that the idea of cosmic inflation is that there have been a very short period when the universe expanded extremely rapidly, in the very first instance of our universe life. It expanded so rapidly that not even light had the possibility to stay behind the expansion of the universe. A sort of cosmic horizon forms, and these cosmic horizons emits quantum excitations of massless modes that are the gravitational waves. So if inflation is correct, putting together quantum mechanics and cosmology, then it means that in our universe is filled up with a background of gravitational waves that come from everywhere, with certain properties that we didn't detect yet. So this is a prediction of inflation. Inflation does a lot of nice things. It makes this prediction that so far have not been tested. And this is one of the sources of gravitational waves that is super interesting to try to look after. So this kind of background has some anisotropies. Well, it comes from everywhere, a background of gravitational waves. With LISA, with the space-based experiment that I told you before, what is nice is that some models of this cosmic inflation predict a background of gravitational waves with an amplitude that can be detected with this experiment. I don't want to enter into the technical details, but this is an example. This is an example of ways to detect the gravitational waves that come from the initial conditions of our universe. So let me also tell you other possibilities to use pulsar timing arrays. So past year, I told you there have been published data by a collaboration that is called Nanograv that claim to maybe they have seen gravitational waves. They don't know the source. They have seen a background of gravitational waves without specifying the source. Okay, early universe models of inflation can fit well the data that are provided by this pulsar timing array collaboration. So this is an example of how gravitational waves can tell us something about the early universe cosmology. Another topic that now is very well studied in gravitational wave physics is the topic of dark matter. Dark matter, I hope you remember, is one of the big mysteries about our universe content, is some form of matter that does not interact with light. Normal matter, since we see each other, we know it interacts with light. Dark matter doesn't and makes up a good fraction of our universe content. So Hawking in the 70s proposed that dark matter is made of black holes. Or made of black holes, but not astrophysical black holes that are the end, that are the end of life of astrophysical objects, but black holes that he called primordial black holes that are formed in the very early universe, for example, during the period of inflation, of cosmic inflation that I was telling to you before. Okay, so Hawking proposed that, that there are many primordial black holes that form dark matter. And of course, since they are black holes, they do not interact with light because they eat up all the light that, they encounter. Okay, so after a few years of study, we know that primordial black holes cannot be all the dark matter. Dark matter should be, if primordial black holes contribute to dark matter, they contribute to a fraction of dark matter. But what is interesting is that gravitational waves can tell us a lot about, if primordial black holes exist, they can tell us a lot about them because the gravitational waves that they form, they can be detected with future gravitational wave experiments, precisely with the experimental LISA that I told you. Why? Because in blue and in red, you see some predictions about the properties of gravitational waves produced by primordial black holes, and they fit well within what are called sensitivity curves of the LISA experiment. So, last topic that I want to tell you is about dark energy, about the last big question mark about our universe content, that is this fluid that makes 70% of our universe. That what do we know about it? We know that it makes our universe not only expand, but expands at an accelerated rate. If dark energy has some properties, in the future our universe will open up more and more, will accelerate more and more, and that's it. If instead dark energy has other properties, we don't really know. It depends on the theory under consideration. So what is dark energy? So Einstein had, for completely different reasons, passed in around 1915, 1920s, Einstein proposed to modify, to add to his general relativity, to his Einstein equations, a piece that is called cosmological constant, lambda, for his own reasons, because he had some incomplete knowledge about cosmology then. Okay, but then he decides to forget about this cosmological constant lambda. But at the end, around 1997, 1998, by studying the light from very distant supernovae that correspond to explosions of stars, people realized that two things, that first, our universe expands to an accelerated rate, and the best way to explain this fact is to reintroduce the cosmological constant lambda of Einstein. The past 20 years, there have been a lot of activity to try both to confirm these cosmological observations, and also at the theory level to try to find alternatives to this lambda. Maybe what makes our universe accelerate is not a constant, but it is some additional force, a long-range cosmological force that it is not constant, and maybe in the future our universe will not accelerate anymore, will just expand or maybe contract. We don't know. There are many ideas in the market, and cosmologists are trying to check them, Gravitational waves will be a super important tool to check these ideas because gravitational waves interact extremely weakly with matter. So if we detect gravitational waves from very distant sources, then it will be great because we will get information about the very distant universe that information that we cannot get from electromagnetic probes only. Within the LISA collaboration, we did some study of what happens if we detect gravitational waves from merging galaxies that are super far away at very, very, very large distances. Gravitational waves from, if two galaxies merge, at the center of each galaxy there are supermassive black holes of masses of order million of solar mass. They emit super loud gravitational wave signals, and LISA is exactly in the right frequency to detect these signals. These signals allows us to confirm or to show that many of the dark energy theories that people are studying, whether they are correct or not. So what we are doing now are forecasts for future detections. Okay, so I think I am done. So in the next decades, there will be an exciting times for gravitational wave cosmology. There are big mysteries in our universe, but there are also a lot of opportunities that are already and that will be. This is very important both for theoretical physicists and for experimental physicists to try to exploit these opportunities. And hopefully, we will find some of the solutions for the big mysteries of our universe. Okay, so thanks a lot. Thanks.
Thank you very much. I keep forgetting that. If I can put it on. All right, good. Thank you very much, Gianmassimo. I think it's reassuring that Earth is not going to be isolated very soon from others. So we probably have a couple of questions, time for a couple of questions. So open up for this, Brian.
Gianmassimo, you talked about merging galaxies.
But, yeah.
What are the frequencies of the gravitational waves from those kinds of events comparable to the frequencies that people have detected?
No, not now. Yeah, indeed. So with LIGO, with LIGO, you get frequencies of order 10, 100 hertz. You cannot go lower because there are seismic noise, there are sorts of noise that you cannot overcome in the Earth. Frequencies of these supermassive black holes, the merging galaxies, are exactly of the order 10 to the minus 4 hertz. So this was the main motivation. So you see also in the picture there. So this was the main motivation for LISA. After that, so these are the frequency range of LISA. So in red, you see the behavior of gravitational waves from merging or supermassive black holes, from merging galaxies. So you see that the signal is not just a point because these objects are merging. So as they merge, they change the orbit start to collapse by emitting gravitational waves up to the end when there is the little chirp signal that says there is collapse. So LISA is built precisely in these frequencies, in the frequencies that will detect these supermassive black holes. So for cosmology, it is interesting for the early universe, etc., but it is also, above all, interesting for studying dark energy. Because if we detect signals from such distant objects in redshift, just to tell you, so let's go a little bit technical, is around redshift 5, 6. So they are claiming this kind of redshifts. There are very few electromagnetic probes that can probe these redshifts. So the hope is to distinguish different models of dark energy. So it is important not only for astrophysics, but also for cosmology.
Are the three nodes like physically connected? Or
No. So there will be laser beams. So I go. There will be, so this is the picture. So there will be three separate spacecrafts that travel in that triangle. There will be an extremely precise knowledge of the position of those spacecraft. I heard, okay, experimentalists, okay, they are 2.5 million kilometers apart. They send laser beams from one to the other. There are ways to not to lose the lasers along the way. And they will control their position with the precision of the meter. Oh. So it is incredible, but this is what they need and what they will do. So this is not only, let me stress, it is not only fantasy. In 2015, there had been an experiment that is, that they sent a sort of toy model in the space of this, and it worked very well. It was called LISA Pathfinder, you find in Google.
Incredibly long
Yeah.
distances. I think you need a very long rod to connect physically.
Yeah, with lasers you can do.
Right. Can I quickly ask you, you have these two. One is expanding, obviously. We all kind of know from the National Geographic and other channels. It's expansion is accelerating. And you also have potential collapse.
So this depends on the curvature. So let me show. This depends on the curvature, on a parameter that is called curvature of our universe. There are cosmological solutions that show that the universe, after a while, it can start to contract. These are not well, let us say, experiments now do not favor this possibility, and there are also theoretical reasons for not believing too much, but it is a possibility that is important to exclude.
It's quite hard for me to imagine how it will come back, with my naive hat on.
The equations of cosmology allow this kind of solutions, allow this kind of configurations.
Well, thanks very much. I think if there are no further questions, Gianmassimo, thank you very much for a wonderful talk. As before, I think we have a very small token of appreciation from the faculty. It's a Welsh crystal engraved with your name.
Thank you very much.
To cherish, to give it to your grandchildren, perhaps, in the future to look at it. Thank you very much.
Thanks. Thank you.